Yeah, it's now up to.
Did we find it?
So, I mean, to introduce Christos Aneziris is maybe not necessary. I'll love to do it if, of course, again, is that beginning? Yeah. Yeah, Christos, well known in our field of refractories and high temperature materials, professor in Freiberg. And as I said this morning, we are now in a bit cross-sectional topics, and he will give about, let's, advanced techniques. This is the session now, and I'm glad that he shows, and we know that you are always beyond some general state-of-the-art techniques. So it's now about additive manufacturing. Your stage.
And not only. I have a lot of slides, but I have the opportunity tomorrow with my colleagues now and my staff that you saw the hardware to pick it up in your hands now and smell it and breathe it in you. So I'm going a little bit faster in some issues, but I would like to underline one special moment of my career. I had done 1991 my master thesis at John when John was at Nottingham. So John has inspired me to use microwaves, and we will see some issues today based on this performance of microwaves, but as it is. Yes, research of the refractories, it was great yesterday. My colleagues showed, also Dietmar, Mark, Jacques, showed excellent fundamentals. How is it working? Why is it working? And of course, yes, we have challenges, because we need high temperatures to be sintered. That means we need a lot of energy, and if you need a lot of energy, CO2 and other issues. So we have to be much more effective, material and energy efficient, yes. So today I will show you some special structures like lightweight design. Lightweight design, yes, because on the one way we have big masses, but can I make a composite system? That means thin wall, fine grained, in a big coarse grained system. So a kind of marriage to combine properties. And of course, we are going also to deal a little bit with hybrid electrification approaches, and you will see some issues today. And we do not de-estimate the recycling. Not only the recycling of our materials, but also the recycling and upcycling in means of refractories from other sources. So for someone, it could be dirty, but for us, it's a gift. Yes, we see here a stopper, as we are doing in Freiberg, a self-glazing system or a pressure slip casted spider brick. You see, we have coarse grain systems now, and the coarse grains can become much more higher. And of course, somebody would say, on the one hand, you deal with corrosion erosion. This is positive. Creep is positive. The coarse grains shrinkage is one very important issue. Imagine we don't speak about small samples, but bigger samples in metal. And especially everything that deals with thermal shock, we have seen yesterday very nicely the impact of pore size distribution, pore morphology. So one key in order to combine, to get the compromise, is the porosity and how you can distribute it. Yes, with pores or with micro cracks that I can create, I can improve the thermal shock performance, but especially if I need a pure material, for instance, like alumina, if I want to have a gas burner, not so high temperatures in means of 2000, 3000, but let's see, we are in the range of H for hydrogen firing, then I need pure alumina, and I have to get an improved thermal shock performance. So on the one way, yes, micro cracks. On the other way, can I integrate heating elements in my gas burner in order to improve? Because thermal gradient means thermal conductivity. It means from heating from inside to outside. So the trip has started, environmental friendly, sustainable, and efficient. And we need the young guys to get this trip together to Ithaca. It's not a labyrinth. We need the new ideas to succeed. And everything is flowing. These are some projects I'm going to saw some results of the German Scientific Foundation, but as well as with some industrial guys. And I would like to start 2009. There's also the name Fire. Some guys from Fire, the real Fire, said, oh, this is the German Fire. No. It's in German, Feuerfest-Initiative zur Reduzierung von Emissionen, refractory initiations to reduce emissions. And we have dealt, for instance, with alumina, zirconia, titania systems. And yesterday we saw very nice the aluminum titanate, how it behaves. It dances, it breathes when you heat up and when you cool down. But in this case, we just formed aluminum titanate in situ and decomposed it during thermal shock. Because then you have volume expansions or shrinkage in volume percent. So these are granites that explode and make microcrack patterns. Of course, you have to control the things. Also, yesterday, Alexander Michaelis showed you the world, the universe of solid oxide fuel cells, electrolyzers, and all these kind of things. And once again, to underline it, we are here in the refractories, but functional ceramics and metal ceramic composites are the key issues for the transformation of the energy. And of course, we can combine these issues with our materials. Somebody would say, how? For instance, in Freiberg, we are dealing with recycling of such kind of electrolyzers. Yes, we can print, we make our own filaments. Here you can see a recycled, printed solid oxide fuel cell. But again, we have some issues with contaminations, which do not give the efficiency. Yes, we are interested in the scandium zirconium or lanthanum sodium manganate in this kind of issues. And somebody would say, how do you mean it in means of refractories? I can add it in a carbon bonded electrode system or a stopper or whatever. And what we see here is the refractoriness under load. The red one is a carbon bonded alumina with 2% recycled lanthanum sodium manganate. And the blue curve is the traditional carbon bonded alumina with 30% approximately, plus antioxidants in means of something like 4% silicon. Pyrolyzed at 800 degrees, pyrolyzed at 600 degrees. And we see if we add the lanthanum strontium manganate, we can avoid silicon metal, and we can also go 200 Kelvin lower with the temperature. So reactions that help us. If you say additive manufacturing, we have started, we didn't call it additive manufacturing, but it was something like a 2.5D with making spaghettis, not pizzas, spaghettis. And somebody would say, why spaghettis 400 millimeters? Because we wanted to filtrate pig iron. And as bigger, the filtration capacity is much higher. It was an extruded issue, and it was based on silicon carbide. Of course, you can do it also with zirconia, but keep in mind, silicon carbide is an electric conductive material, semiconductor, as well as at elevated temperatures. Also, zirconia above 1000 degrees Celsius, it becomes electric conductive. Yes, we have also the oxygen and all these kind of issues, but these are functional materials. We can activate them. And keep in mind, aluminum oxide, above 1000 degrees Celsius, you have 10 power to 4 higher electrical conductivity. So these are issues in order to meet the demands for going to smart refractories, as Hong Peng yesterday mentioned. Okay, 2024, my guys are experts today to print filaments or based on filaments. Of course, you can cut also the filaments and go to pellets. And it's much more easier because you don't need the flexibility of the filament. And as you know, our materials based are not flexible. And in this kind of issue, you can use much less binder. You will see this tomorrow, how we can print or how the printer is. You can make our own filaments, but keep in mind, granulates or pellets, much less binder. So on the one way, and one basic issue for us is we can make a thermal debinding, not a chemical debinding. So guys who are dealing with debinding, this is a very interesting issue. Of course, you have to meet the demands of tolerances. So you see, and now we are printing. So in order to meet the tolerances, you have, yes, It has to dance. It has to go where you want to go, no? But not so much. And please stop the dancing now when the music stops. So this is one very interesting issue. So you have to add additives, no, in order to control. And somebody would say, why are you doing 3D? No? I'm doing the 3D not only to mix or to have the freedom of shapes. No. Me as a refractory guy, I can position the pores where I want. I can position the pore habitus as I want and where I want. This is the key for us. We are not experts to make very high dense structures. This is not the key. Yes, we want to make macro pores, macro channels, where I have to be tight, high density, corrosion, erosion resistance, yes, B. But the structure behind, it could be not so dense, in order to be able to withstand the thermal shocks. No? Play with materials. We see you can make steel inside if you want to fix it with an anchor, and outside makes a ceramic. And of course, as John mentioned, you will have a distribution, yes, of the phases, which as a gradient structure could withstand thermal shocks. Let's have a nozzle. If you see the nozzle in this area here, it's a computer tomography picture. You have some holes. These are functional holes. We speak about functional porosity. And somebody would say, why? We will immediately see the why. Of course, up to coming to this moment, you can make arts in the beginning, as we see it on the left. Perhaps the price is much higher from the original. But at the end of the day, if you control the debinding and especially the sintering, yes, you can create such kind of nozzles after printing, after sintering. You have an inside with special properties. You have a light structure between the outer, and of course, we know you can. It could be that the outer is like a belt and put under compression the inside, so you improve the thermal shock performance on the one way. On the other way, we have a filament, so layer by layer, and this is something like the aragonite structure. And if I can also make micro cracks, we know from the flame spraying processing, I have excellent thermal shock performance. Okay. Yes, today the printer guys, they can print pore structure, and then you can also machine in green stage. So you have the porosity where you would like to have it, and you can close the pores via machining. And high speed. And then, of course, if we have make the piece, I have a fine-grained refractory material, and I have integrated in a coarse-grained refractory material. I'm going to the steel casting simulator that we have in Freiberg, you'll see it tomorrow. Yes, it's a drop in the ocean. It's only 100 kilograms that we can melt, but we can select all the insides and outsides as we wish. We can design the steel. This is very important. And somebody would say, okay, nice talking. Do you survive? Yes, we survive. So steel melt in full controlled atmosphere, so we know what we are doing, hopefully. And we see that we survive. A pure oxide, and it was a spinel. It was an alumina Almatis 78 spinel. Survived. It was a fiber-free, because they burn fire out, carbon-free. Yes, we are dealing also with carbon-bonded alumina, but we put self-glazing systems. Silicon carbide-free and silica-free. And yes, if you survive, is it perhaps a material or with a processing route for hydrogen burners or for plasma burners? Plasma burners we will see immediately. And somebody would say, is the technology very difficult? No, it's the normal ceramic technology as we know it when we make extrusion, okay, with filaments, and then we go to printing and debind pieces. Some pictures, yes, you can play and you can use artificial intelligence to create structures, and so it's fantastic, but okay, it should have a meaning, how many layers you do, why you do it, and keep in mind costs, energy, and so on. And at the end of the day, you want a functional product. And I will stay to zirconia. And we see also ECerS, it's a project with Chris, because zirconia is a very fantastic material. We know monoclinic, tetragonal, cubic. The question is, what kind of phases do you really need? Not a fully stabilized, no? You need a high amount of tetragonal and tetragonal metastable so that you can create, when you need it, cracks. Of course, you have always to pay attention. You have at 1170, for instance, in a special system, the transformation for monoclinic to tetragonal or tetragonal to monoclinic. Do my microcracks that I have created are they still there or are they healed? So you have always to create microcracks, but you have to keep in mind, I want to have them when I need them. Take a part of a sub-percent entry nozzle. It's first preheated up to 1100. Then it moves to the casting machine. It goes down to 900. And then you have a thermal shock upstairs, to 1600 when the melt comes. So this is what we have to design. This kind of thermal shock you have designed. And the microcracks, when you go from 900 to 1600, from some of them are going to be healed. So you have to design to get structures which still remain and contribute in means of the thermal shock performance. And of course, you have to keep in mind, it's a product, after it has been used, it's going to lose its neck. It's a one-way product. It's not going up and down like a ladle. So completely other design, and keep all this always in mind. Yes, you can play with the zirconias and you see a double kind of stabilization. Why? Because we have found out that the tetragonal is very important. Yes, you have also, based on the monoclinic, created to the expansion, you have created granates of monoclinic. Yes, but you lose them when you increase the temperature, some of them. So you need them and you have to trigger them when you really need them. And during sintering, you lose some of the stabilizing agent. So you want to have a support of the other stabilizing agent and get in touch with something else which also improves the compression. Somebody would say, how do you know this? Yes, you can use EBSD, electrobaxatic diffraction, yes, and you can, in the scanning electron microscope, identify the phases. So the tools as they were when I did my thesis are today in such kind of state what I would say I would like once again to study. Yes, you survive thermal shock, and you several times survive the thermal shock, in spite of the fact that it is a fine-grained zirconia material as it is used in solid oxide fuel cells. Of course, not scandium and this kind of things. It's magnesium or calcium or yttrium. And of course, you can design everything that you need. This is a fused alumina system. You can make nozzles, crucibles, and you survive. And keep in mind, we do not want a high strength. Strength is below the ratio to the R4 parameter according to Hasselmann. It's power to 2. It's a negative impact. We want pores, but the pores have to be designed. And if we speak about pores, sorry, here. Yes, if we speak about pores, yes, why do we not make functional porous ceramics for advancing temperatures in means environments or so chemical attack? And Alexander yesterday showed also the impact of NH3 as a source for H2. Somebody would say, is it an easy issue? And why do you want a special gyroid structure? It's not a foaming structure, it's a gyroid structure. Why? Because if you put air and directly NH3 to fire H2, you will getting a much higher amount of NOx. And you don't want to say CO2 out, but NOx high. So you have to get a compromise of the processing issue. And it's not only a gyroidal structure, it's several pore structures have to be combined, have to be engineered by young guys like you in order to meet the demands of the combustion. And you have to do it not only fine-grained, you have to do it also coarse-grained. Because you don't need only small issues, you need also big issues. Yes, again, you can print, you can pelletize, you can make some kind of gyroidal structures. But of course, you can use also two nozzles. It's going to change because I want to have, for instance, alumina. Alumina is the material, but I want to put silicon carbide in the inside in order to improve the thermal shock performance. Or I want to put an AZT system. And we see here the behavior, the crack resistance of this material, where we have added 2.5 magnesium stabilized zircon and 2.5 point titanium. And we see this kind of behavior, not the classical, as we have it in ceramics. So it's like a spong according to the heat, the mechanical stressing of the material. And of course, if you have good materials in means of thermal shock, you can also think, yes, let's go with pure aluminum and make H2 approaches. I've spoken about microwave plasma burners. Somebody would say, why? On the one way, it's a direct use of electrical energy, so I don't have to transform it. Yes, if I have to store, but I want to use it immediately. We do not have a microwave coupling, as we did it in 1991 when I was the John in Nottingham. We only heat the air, like a CH4 burner. And we do not need any cathodes. It's a little bit loud, but it's an easy approach, something like 6 kilowatts. We have started with this system. Of course, somebody would say 6 kilowatts, it's not enough. You have to increase. And of course, we want to go to this technology, and not only microwave plasma, but also induction plasma and so on. Why? Because sintering is the most energy intensive process with approximately 70% of the whole energy consumption. And keep always in mind, if you have a tunnel kiln, only 10 to 15% goes to your component. Everything else are losses. Of course, if we are going to be successful, we would like to put it at an industrial kiln to see how we go from the laboratory to an really industrial application. And the red arrows that you see here are 65 CH4 burners. Of course, we want successive, step by step to do it. Somebody would say, why? The why we have seen it yesterday, because when we have H2 atmosphere, we are H2O atmospheres. And we have seen here in 2008 the impact that if we have not used pure aluminas, but also alumina silicate systems, above 1400 degrees, everything goes in the air. What we have done is we have made a pre-treatment of original MgO-based bricks for the cement rotary kiln, and we have used 200, 400, 600 degrees temperature in a pre-treatment, natural gas 100%, 100% hydrogen, the blue ones, and a 50-50. And then we have fired them in the Refratechnik kiln that you saw before at 1600 degrees Celsius. What we have seen is, pay attention, above 400, especially above 600, we lose more than 40% of the splitting, based on the splitting test, the strength. And you can imagine this is something like 7 to 8 kilogram brick, and after 1 week, you lose bricks in a rotary kiln. This is a disaster. I would only to also underline, pay attention, the 200 degrees pre-treatment, the hydrogen gave us very high strengths. If you go to the paper, you will see, based on differential thermal analysis, that the peaks of the calcium silicate formation or changing, also the brucite formation, have been a little bit shifted. It's not only thermodynamics, it's kinetic and thermodynamics. Okay, yes, the small one, the 6 kilowatt was above. Of course, we have also microwave, and we have approximately 1 cubic meter furnace. We have a 100 kilowatt microwave plasma burner, 65 CH4, and electrical molybdenum disilicide heaters, so electrical heating elements. It's the same trick as Bengt did yesterday. She can move the pictures. So the picture has to be like this. We have done this. Marie Oppelt and Christine Dietzer have dealt with a little bit with magnesia. We are in the same area of strengths. I don't want to go further. We have fired Tozo 1.5 yttria stabilized tetragonal zirconia, no? So a high-tech ceramic. And we have seen we can heat faster. And not only this, keep in mind, I have a burner who is circulating the temperature. The other was conventional heating elements. Can I go to a continuous kiln? Question mark. And also, we see here gas burner, clay bricks or tiles, no? Electrical heating elements, and plasma burner. And if you have a telescope, you could see here we are creating stars, so needle-like structures. Can we improve the K1C at room temperature? Can we improve the strength? Then I can get a lighter weight of the tiles, of the roof tiles. No? As well as we have treated some bricks, alumina-rich bricks, which were in contact with a melt, iron melt, steel melt, and we have seen we have much lower wettability. We have 10 plus, increase the wetting angle. Somebody would say why? Because the plasma burner has NOx, the plasma burner has O3. The plasma burner creates radicals. You always have to have, on the one way, is positive issues, but it could be also bad issues. No? NOx, healthy, no? Ozone is not also nice. No? It smells like a chlorine environment. No? Okay. Yes, wind energy is very important here in Germany, in Europe, in all the world. Germany created 138 terawatt hours. And of course, these kind of miles are very, very important. And we had a so-called collaborative research center in which we tried to filtrate the steel melt in order to perform excellent mechanical properties of the bonding. Somebody would say, what was triggering this? It was an accident that happened in the ice train 2008, where very nice, dense, fine aluminas in the range of 200 up to 400 micrometers could not be removed out of the wheel, and so we had the damage. I suppose 8 months, the ice tree was in whole Germany, not moving. This was good for us because we got a project. We're under a focal mechanic microscope. This is in the Steel Institute. Professor Volkova, but the guys are here also. And we have placed an alumina, and this alumina catches the small alumina in situ inclusions. And this was the starting point where we say, okay, let's put the same chemistry in order to pick up the same chemistry of the inclusions that are created in the steel. Of course, you can the steel melt can be cured through the filter, or you can use also carbon bonded alumina and you make bubbling in the melt. And then you can, via buoyancy forces, select and pick up like a porous plug is doing. Of course, you have to design the structure. You have to put in the carbon bonded alumina. So this is a carbon bonded alumina. You have to put on the top aluminum oxide, but you have to pay attention not to cinder it very tight, because you want to breathe with the melt, to have an exchange with the melt. Of course, if you are young, not me, my colleagues, my staff. Yes, you can print sugar or you can print salt via 3D printing. And then you can go via flame spraying and create the structure. Somebody would say, why? Because I can wash it out and I do not have to burn out the polyurethane foam, the template. And you have also flame spraying, you are going to see it with the robotics. So you can not only make thermal shock, you can create some structures. And then you go to the steel casting simulator and you survive. And of course, you have to go today with in situ with focused iron beam in order to be able to characterize much deeper this kind of layers that are created and are collecting the deposit. In this case, a positive. Emmanuel showed yesterday a bad deposit. Here is a good deposit because we pick up the ceramics out of the melt and we deposit on the ceramic. It's a very interesting issue because only this number, yes, you can filtrate up to 95% of the hard alumina inclusions in a steel melt. The fantasy is free. You can generate a cosmos or a universe, as we say. And of course, you have to go also to the next step. You have to say, okay, let's go to a step where we can apply it in a steel plant. So yes, it has happened. It works. So this was the filter package so that we can go via the slack line and not destroy in the slack line. So we want to collect inclusions. The steel plant, I only will show when it comes up, so it's a right. And it survived because the deposits, that means the inclusions, sealed the carbon bonded alumina. So you can use the chemistry in order to improve the performance of your component. The bad things, combine it for the good things. Okay, let's go from the recycling of metals to recycling of refractories. It was already mentioned yesterday, according to McCarbon bricks, for instance. And we have 20 guys here with you that belong to a school of the DFG of this 2802. This is a number. But the number means that half of them are dealing with recycling. That means they pick up MgOC refractories and they combine them with environmental friendly binders. So no pitch, no resin. Let's use tannin, fructose, collagen. Do I get residual carbon in the same height? Do I get the strengths after cooking? You can discuss with them today and tomorrow and during the ECerS. And the next idea was, okay, let's pick up the MgOC, make MgO, and make a marriage with steel. We have made in the past, also in another center, metal matrix composites. We have taken zirconia and we have taken a tripped whip steel, and we have made a composite system and we increased the strength and the elongation of the steel via the zirconia destabilization in situ. And then we said, okay, if we can do this, okay, let's pick up magnesium, pick up steel, make again the marriage. Why? Because I wanted to create carbon-free, inert electrodes. They are not inert, they are also reacting for the aluminum electrolysis. So get rid of CF4. Get rid out of CO2. Yes, the recycling is something that it works, but you always have to pay attention. This is magnesia fused. This is magnesia recycled. The grains are becoming much smaller. Porosity is increasing. It's contaminated. And the most important, the calcium to silica ratio is also decreasing. You lose calcium. And you need calcium, the calcium silicate phases and so on, in order to meet the demands of creep. But if you go and measure the inclusions in the steel casting simulator, you see, due to the fact that you have a saturated material, you decrease the interactions. Okay, let's go to the marriage with MgO recyclate with steel. You have to cinder it. Somebody would say, which temperature? Not 1600, the steel is away. 1370, 1400 maximum. Where you cinder it? In argon atmosphere, in a carbon heating element containing furnace. You will see it tomorrow. You cinder, and then you have to pre-oxidize. So you create spinels or other solid solutions, as we saw by Inho Jung. And this can protect or decrease the interactions with the aluminum melt. Keep in mind, when you see the presentation of Alexander, in the anodes, you create, especially in the aluminum electrolysis, oxygen. So you can have also an in situ oxidation of the metal ceramic component. Somebody would say, okay, and where is it? If you use magnesia recyclate and you use also pre-oxidation, where is your conductivity? Because you need a high conductivity, electric conductivity, in order to meet the demands of low energy consumption during the electrolysis. And we see here is carbon, yes? And we are in this area, well, we are not graphite, but we are in a very good area where it could work. And we have here, perhaps you can see him somewhere. Here is it. He's there, and he made with an electrode of the other guy, Serkin, they made aluminum out of it. Or you can make screws and all these kind of things. It's the ceramic technology to a metal ceramic composite system. And these are preheatable electric conductive systems, not for steel applications, but for aluminum. And of course, because we had before John, let's say go to a marriage between refractory composites and material composites in means of getting refractory metals, tantalum and niobium, and put it with alumina. Somebody would say, yes, this is well known. Yes, it's well known, but let's get one puzzle more. Let's make big grains as we have it in the refractory thinking and pre-cinder them. Why? I want to take out the shrinkage. I want to have a pre-sintered product, coarse-grained metalloceramic. And if I do this, I can make big components. I can make big electrodes. I can integrate these electrodes in alumina pure systems. Thilo Tsinat is going to speak Tuesday, Wednesday, I don't remember now. And somebody would say, oh, it's very crazy issue. We have also a guy, Gregory from Kaitene, they measure the electric conductivity. And you see, you need a lot of, not so much niobium in order to get the percolation. That means already electric conductivity by room temperature. And of course, it's a grained issue, with pores, as we know from refractories. You can recyclate them, you can reuse them, and then you have interesting electrodes. You have, via the alginations and xylation, you can print in water. This is nothing else as the chocolate formation. So Conda, you know, these ones are made by this. Or you can make metalloceramic paper. And somebody would say, why are you doing these issues? Yes, because if you have a gas turbine, who have worked a lot of years with the guys, yes, you have the heating seals. The heating seals. Yes, these are aluminum mullite systems. It works up to 1300 degrees in case of normal combustion. But if you go to H2 combustion, you have problems. So you have to get the mullite outside, or you have a heating seal as we do it with a pressure slip caster, and you integrate a 3D heating element. Then you don't have the thermal shock problem, and you can increase the application of the gas turbine. And this is a Carnot gas turbine. It means as higher the temperature, you get a positive impact according to the efficiency. And if you think like this, yes, I showed you in the beginning This is a self-glazing carbon bonded alumina, stopper, electrode, whatever you want to do. What would be if we take the carbon, bond it, and we put it in the inside as an electrode? And we leave alumina outside, because alumina will not have the interactions with the steel and create alumina inclusion. Of course, somebody would say, you have shown us filament 3D printing, and you make bigger things. During ECerS, now there are the groups of Paulo Colombo, Choca, Georgia, and so on. Georgia is also in the Young, was in this special issue now as guest editor that Alexandra showed us. No? And they are doing 3D printing. We have also a 3D printer. And the question would be, can I make 3D printing of 3D printed and printed coarse grains? Because I can design, if I have 3 millimeters, if I have 4 millimeters, I can design my grain. I can put the electric conductive issues, and then I can go and make some special structures, big structures, fast, and so on. I don't want to keep, how much time we have? 2 minutes, 3 minutes? Okay. But let's see the component. Yes, it has to be clean, yes. So they're not the reactive powder, of course. Okay. And closing, I would like to give you some inspiration. Why can we not combine microwave plasma burner with microwave coupling? Somebody would say, what is this? Yes, if you have steel and you put steel in the microwave in your house, now you will have an arc patch. But if the steel is melted or the aluminum is melted, then you have an interaction with microwaves. So what about having a big generator? And this is not a fiction, it's a vision. And having energy microwave power in order to get an ignition and to get as a burner. And when you reach the melting point, you apply microwaves. We are also going to start in November this year with an induction plasma burner, a rotary kiln with induction plasma burner. Somebody would say, why? A lot of the processing routes, cement industry, not only, are dealing. And of course, if you have carbon bonded systems, which have not to be pyrolyzed, or also silicon carbide based systems and other issues, you can put also electrodes and you use them as a heating element during the pyrolysis. So you apply directly the energy where you want. Perhaps you could create also special structures. Yes. It says hypothesis, antithesis, synthesis. We are engineers mainly. That means we have to find a solution. Yes, we have to get to a dialogue. And we are going to get a confrontation. But at the end of the day, I believe all of you, it doesn't matter where you're coming from. You can be inspired and make a synthesis. And it can be a synthesis of new materials, or there can be a synthesis of new processing routes. And at the end of the day, this is ECerS. This is fire. This is the networking. Get the advanced ceramics with functional ceramics to refractories. And from the refractories that we have learned, what could we improve? Thank you very much for your attention and see you tomorrow.
Yeah, thanks, Christos, for this really inspiring view into all the work of, I don't know, some years already, my guess, but I think which is ongoing. Directly questions from the audience here. Victor has one, okay.
Congratulations for the presentation. When you said about the nozzles, the first one, could you compare the price if you do it printed and 3D printed, pressed and 3D printed?
You mean the small nozzles?
Yeah.
The small nozzles. Okay, you cannot compete today, no? You cannot compete, no? Castables. Today it's not possible, no? But if you think that the small nozzle is a fine-grained, that means higher corrosion and erosion resistance in comparison to a coarse-grained castable, no? And of course, you cannot meet the demands, no, of the thermal shock performance. I need this kind of structure, layer by layer, in order to be able to create cracks, no? And cavities as I want them. You would say, okay, let's use a mold which you sacrifice. It's possible, no? That's why we make the porous blacks, no? And so on. But here you can do it much more precisely. You don't sacrifice anything, no? And I have not yet met the demands in this fine-grained issue, no? Especially with zirconia, no? According to the thermal shock demands that or challenge we have. No? This is one main issue. No? Once again, 3D is not for everything. The castables, as we know them in the refractories, it's a unique technology. You can combine it. No? But for special issues, no? Especially if you want to put two materials, so an electric conductive material and a non-conductive material, no? Or you want to make it several layers. We have done it also with paper technology, no? And making nozzles and these kind of things, no? With Peter Gleil and Andreas Rosen and all these guys, no? But at the end of the day, the nozzles that I saw today, no? And let's speak about cost, no? I don't know, let's say X is the cost of the zirconia, so it's the same. You have to pre-mix and make your filament. And of course, you fire out of the filament. That means, let's say, 30% additional, no? So I believe 30% additional costs today. But it's an estimation, yes?
Yeah, it's not,
I've not calculated.
not industrialized. Okay. Yeah, thanks again. I think everybody's ready for coffee. So I hope you enjoy it now. Thanks again. And I think, yeah, we'll meet all together tomorrow in Freiberg. Thanks for this invitation. Okay, thanks a lot and see you in the next section.